Welcome to Best Math and Science Videos, Freefall in One Dimension. In this video, we consider objects in free fall. That is, objects that experience constant acceleration due to the downward force of gravity. We will only consider objects in one dimension. They move vertically down or up. We will look at two-dimensional motion under the force of gravity in another video. Let's look at a free fall question. Paul accidentally drops his cell phone from his apartment balcony. It falls 14.8 meters before hitting the ground. At what velocity did the phone hit the ground? How long did it fall? You should always start by analyzing the problem and, if possible, sketching the situation. So, we have an object that is falling down. Let's choose the coordinate system so that up is in the positive x direction. We can use these variables to describe the situation. Now, consider what information is known. Paul drops the phone. This tells us that the initial velocity is 0. And it also tells us that the acceleration is due to gravity, negative 9.81 meters per second squared. This is negative because we chose upward to be positive. We are also told how far the phone falls. So the displacement delta x equals negative 14.8 meters. This is also negative because upward is positive. And now, what information is unknown? We need to know the velocity of the phone when it hit the ground, Vf. And we need to know how long it fell, delta t. When you solve free fall problems, since the acceleration is constant, you can use the kinematic equations. This is a set of 4 equations that relate the variables of the motion. But which equation should you use? The trick is to choose an equation with only one unknown variable. Notice that both the first equation and the fourth equation have 2 unknowns, final velocity and the time. You can't solve an equation with 2 unknowns, so these equations won't help us. The second equation has only one unknown, time. But notice that it has delta t in the middle term and delta t squared in the last term. We could use this equation, but the squared value of time, one of the unknowns, would make it a little complicated to use. Instead, look at the third equation. It has just one unknown, the final velocity. All the other variables in the equation are known, so this is the equation we want to use. Okay. So now we can solve the problem. First, we substitute the known variables. The initial velocity is 0. The acceleration is negative 9.81 meters per second squared, and the displacement is negative 14.8 meters. Using a calculator, we find that Vf squared equals 290.376 meters squared per second squared. And taking the square root, we find that Vf equals negative 17.0404 meters per second. Remember that square roots have both a positive and a negative answer, and you have to choose the sign depending on the situation. Since the cell phone is falling down, we chose the answer that gave a negative velocity. Also, this is an intermediate answer. We're not quite finished. For the final answer, we need to round to the correct number of significant figures. The values we multiplied have 3 significant figures, so our answer must have 3 as well. Rounding to 3 significant figures, the final velocity of the cell phone is negative 17.0 meters per second. Okay, so now let's answer the second question. How long did the cell phone fall? And again, let's look at the kinematic equations. For this question, we need an equation in which time is the only unknown, so we can use the first equation. We know the final velocity, the initial velocity, and the acceleration. So let's do the calculation. First, we need to rearrange the equation to isolate delta t, and then switch the sides so that delta t is on the left. I want to pause here to show you something that you really need to watch out for when solving these types of problems. Let's finish finding delta t by substituting the final velocity we found before and the acceleration due to gravity. The answer equals 1.73 seconds. However, this answer is wrong. When you solve a problem with multiple calculations, you have to use the intermediate calculation before it is rounded to the correct number of significant figures. When we substitute the intermediate speed, negative 17.0404 meters per second, we find that delta t is 1.74 seconds, and this is the correct answer. The phone hits the ground with a velocity of negative 17.0 meters per second, and it took 1.74 seconds for it to hit the ground. These are your final answer. Next, let's look at a problem in which the initial velocity is not zero. From the flat roof of a building, a ball is thrown downward with an initial velocity of 6.0 meters per second. It hits the ground below 1.6 seconds later. What is the height of the building? First, let's sketch the situation. Let's define the coordinate system so that up is positive. A person is at the top of a building and throws a ball down, giving a ball an initial downward velocity. The ball falls a distance equal to delta x. Remember, delta x is actually the displacement of the ball. It's a vector quantity. It can be either positive or negative. Since the ball is moving down, we know, of course, that delta x will be negative. So let's consider what is known and unknown in the problem. We know that the initial velocity is negative 6.0 meters per second. It's negative because the ball is falling. We also know that the acceleration due to gravity is negative 9.81 meters per second squared. And we know that the time, delta t, is 1.6 seconds. We need to know the height of the building, so that's the unknown. You can see from the diagram that the ball falls a distance of delta x. That is the displacement. The height of the building must be positive, of course, so it must equal negative delta x. We need to find delta x first, so let's look at the kinematic equations. Which of these equations includes only delta x as the unknown? The second one. We know the other variables in this equation: the initial velocity, the time, and the acceleration. So let's use this in our calculation. We can now substitute the known information. The initial velocity is negative 6.0 meters per second. The time is 1.6 seconds. It appears twice in the equation. And the acceleration is negative 9.81 meters per second squared. Using a calculator, we find that delta x is negative 22 meters, which I've rounded to two significant figures. Therefore, the height of the building is negative of this value. So the height of the building is positive 22 meters. And this is your answer. Notice in this problem that it is very important to keep track of the signs. And this shows why defining the coordinate system and having a sketch are important. Okay, let's look now at a problem in which an object is thrown upward. Zoe threw a coin straight up into the air with an initial upward velocity of 3.15 meters per second. The coin's initial height was 1.1 meters. What maximum height did the coin reach? Let's sketch the situation. First, define the coordinate system so that up is positive. Zoe threw the coin straight up with an initial velocity vi, which we know is 3.15 meters per second. And she threw it from an initial height xi, which we know is 1.1 meters above the ground. Gravity is pulling down on the coin, and the coin moves up to a final height of xf before falling back down. So let's look at what we know. We know that the initial velocity is 3.15 meters per second. It is positive because we define upward as positive. And we know the coin's initial height, xi, is 1.1 meters. And as the coin is moving upward, the only force on it is gravity. So its acceleration is negative 9.81 meters per second squared. We also know that at its maximum height, the coin's velocity, Vf, is 0. This isn't stated in the problem, but we know it must be true because the coin must stop momentarily before falling back down. And what is unknown? We need to find the coin's maximum height, xf. Let's now choose a kinematic equation for the calculation. This time, the choice is easy. We don't know the time delta t, so we can't use the first, second, or fourth equation. We can only use the third equation, which doesn't include delta t. So let's look at this equation. Before you start your calculations, always look to see if you can simplify the equation. In this case, notice that we have Vf in the equation, which we know is 0. Also, notice that the equation has delta x. Remember that delta means the change in something, so delta x is xf minus xi. We can use both of these facts to simplify the equation. So remember, you first choose your kinematic equation. Then you simplify it if possible. And next, solve the equation for the variable that is unknown, in this case, xf. To do this, let's first subtract vi squared from each side, and then divide by 2a, and rearrange to have xf by itself on the left side. So this is now in the form of the equation we can solve for our answer. First, insert the known values. xi equals 1.1 meters. Vi equals 3.15 meters per second. And a equals negative 9.81 meters per second squared. Using a calculator, we find that xf equals 1.1 meters plus 0.506 meters. Before we write the final answer, let's think about the rules of significant figures. When you add or subtract numbers, the result must have the same number of digits to the right of the decimal as the number with the fewest digits to the right of the decimal. The first number we are adding has just one digit to the right of the decimal point. The second number has 3 digits to the right of the decimal point. So our answer must be written with just 1 digit to the right of the decimal. So back to the calculation. Adding, we find that xf equals 1.6 meters. This correctly has just 1 digit to the right of the decimal. And this is your answer. The coin reached a maximum height of 1.6 meters. Remember that the coin's original height was 1.1 meters, so the final height of 1.6 meters is reasonable. Okay, let's look at one last problem. This one is a little more difficult. A baseball player hits a foul ball upward from a starting height of 1.50 meters. The ball reaches a maximum height of 34.5 meters before falling to the ground. How long does the ball stay in the air? Let's sketch the situation, and we'll choose up as the positive direction. The ball travels straight up from a height of xi to a maximum height. Let's label this x top. And we know the ball then falls down to the ground below. We want to know how long the ball stays in the air. For a problem in which the object moves up and then down, it's often easiest to solve the problem in 2 parts. So the total time is the sum of the time up and the time down. Let's consider what we know. The starting height, xi, is 1.50 meters. The maximum height of the ball, x top, is 34.5 meters. And the velocity of the ball at this height, v top, is 0. The ground height, of course, is 0. And the ball's acceleration is constant, negative 9.81 meters per second squared. And what is unknown? We want to know how long the ball stays in the air. So the unknown is delta t total, the sum of the time up and the time down. The first step then is to find the time it takes the ball to move upward, t up. So let's look at the kinematic equations. Our unknown is delta t, which for step 1 is t up. So delta t must be the only unknown in the equation we use. The first, second, and last equations all have delta t, but notice that each of these equations also includes vi, the initial velocity, when the player throws the ball up. We don't know this velocity, and we can't solve an equation with two unknowns, so we can't use these equations. Now look at the third equation. This equation does not contain delta t, which is what we want to find. However, we do know all of the variables except vi. So for step 1, we can first use the third equation to find vi. And then use vi in the first equation to find t up, the time for the ball to rise. So let's start with the third equation, rewriting using v top as the final velocity. V top squared equals vi squared plus 2a delta x. Can we simplify this equation? We know that v top equals 0, and we know that the displacement delta x equals the final position x top minus the starting position xi. So let's use these to rewrite the equation. Now let's rearrange the equation with vi squared by itself on the left, and take the square root. It might concern you that we have a negative sign under the square root. Remember, however, that the acceleration is negative, so the entire expression will be positive. Let's now substitute the given values. Acceleration is negative 9.81 meters per second squared. X top equals 34.5 meters. And xi equals 1.50 meters. Using a calculator and taking the square root, we get vi equals 25.4452 meters per second. Remember that this is an intermediate value. We won't round to the correct number of significant figures until the end. Okay, now that we know vi, let's use it to calculate t up, the time for the ball to rise to its maximum height. So which kinematic equation should we use? We should use the first one. We know the final velocity and the initial velocity as the ball is rising. And we know the acceleration, so the time is the only unknown. So let's write this equation, replacing delta t with t up and replacing vf, the final velocity during this time, with v top. Here again we can simplify because we know that v top, the velocity at the top of the ball's path, is 0. So we can rewrite the simplified equation. And now rearrange it to solve for t up. Substitute the known values of vi and acceleration, and using a calculator gives the time for the ball to rise as 2.5938 seconds. So here again, this is an intermediate value. We need to find the total time before rounding to the correct number of significant figures. However, I want to point out something here. Remember that the original values were stated with 3 significant figures. So if this were our final answer, we would also have 3 significant figures. So I'll put a line under the 9 to indicate this. But since this is an intermediate value, we need to keep the extra digits for now. Now, step 2 is to find t down, the time it takes the ball to move from its highest point to the ground. This is solved almost the same way. Again, looking at the kinematic equations, you can use the third equation, this time to find vf, and then use vf to find the time for the ball to fall to the ground. So we start by writing the third equation, but we are only dealing with the time during which the ball is falling. So the initial velocity is 0, and the displacement delta x is the final position x ground minus the initial position x top. And we know that x ground is 0. So let's rewrite the equation to solve for vf. Remember, the square root can be either positive or negative. Substituting the values for a and x top and using the calculator, we get vf equals minus 26.01711 meters per second. Here again, this is an intermediate value. We won't round to the correct significant figures yet. And we chose the negative value because when the ball is falling, its velocity when it hits the ground will be downward, which is negative. Okay, so now that we know vf, let's use it to find t down. This is done using the same procedure as before. This time, we know that the initial velocity as the ball falls is 0, so we can rearrange the first kinematic equation to get t down equals vf divided by the acceleration. And substituting the known values for vf and the acceleration, we get t down equals 2.6521 seconds. And here again, if this were the final value, we would round it to 3 significant figures. So I'll place a line under the 5 to indicate that, but we'll carry the extra digits since this is an intermediate value. So now, the total time that the ball was in the air is t up plus t down. So, substituting these values, we get t total equals 5.25 seconds, which is rounded to the hundredths place, like both of the numbers we've added. And this is your answer. The baseball stayed in the air 5.25 seconds. This video has shown you how to solve free-fall and one-dimension problems. This topic can be confusing. I urge you to watch the video again and pause to review parts you find challenging. Then, watch these related videos, Free-fall in 2 dimensions, and significant figures. I'll put a link below. You can learn a lot from Best Math and Science videos. We're always posting lots of great videos. Click to subscribe so you don't miss any of them. Thanks for watching. See you next time.